In this lecture, we're going to continue on talking about generating functions. And if you remember where we ended last lecture, we were talking about the generating function for rooted binary trees. So they're binary trees that had some root and then some children, either 0, 1, or 2 children. So here's an example of a binary rooted tree. And where we ended up is we wrote down our recursion in terms of the generating function to build all binary trees. We said you start with a root, and then on that root you can either have nothing, you can have a branch to the left, you can have a branch to the right, or you can have a branch to the left and right. And so from that idea, we wrote down an equation that the generating function must satisfy. And I just want to say this is for non-empty rooted binary trees, but that's okay. We want to eventually get to all binary trees, all rooted binary trees, but we're just missing the empty one. So we'll just we'll call all of them t star of x, and we'll take all of them that we have for non-empty ones, and we'll just add that one empty one of degree 0. So that's a very easy relationship. This is just an easier way to look at it in order to build this recursion. Okay. So now we're just going to do a little bit of algebra here to solve for t of x. You can see here we have t of x all squared, so you can imagine we'll have to do the quadratic formula at some point. So let's multiply through by x, so we get x times xtx plus xtx, that's 2x tx's, plus x times tx all squared. And now we're just going to move everything over to one side. In fact, that side is going to be the left-hand side, but then we'll just write it on the right. So we're just solving for the right-hand side, even though I wrote it on the left-hand side here. So the only thing that comes over is that t of x. So instead of having 2x t of x's, we have 2x minus 1 t of x's. Okay, good stuff. So now we're thinking about t of x here as our variable. So we have t of x, something t of x squared plus something t of x plus a constant equals 0. So we're going to use the quadratic formula to solve for t of x. So negative b, so that's 1 minus 2x, plus or minus b squared plus or minus 2x minus 1 squared, minus 4ac, so minus 4 times x, so that's 4x squared, all over 2a, all over 2x. Good stuff. And we can simplify what's in the square root here. This simplifies to 4x squared minus 4x plus 1. So the 4x squared cancels with this negative 4x squared, and we're just left with negative 4x plus 1, which I'll write as 1 minus 4x. So you can see here, because we're using the quadratic formula, we have a plus or minus. And obviously the generating function is only going to be one of these, so we have to determine which one. And if you remember, we want that our generating functions are convergent somewhere. So we want them to be convergent somewhere near x equals 0. So let's take the limit as x equals 0 when we have the plus and when we have the minus, and let's see what happens. So for the first, if we have the plus here, you can check via, I don't know, L'Hopital's rule or something like that, that this limit indeed does not exist. But also you can check via L'Hopital's rule or something like that this limit is indeed 0. So to make sure we have a generating function that converges somewhere, this is the generating function we're going to go with. So we have our generating function for non-empty rooted binary trees, given by this formula here. And we're just going to add 1 to it to get all binary trees, all rooted binary trees, including the empty tree. So I'm going to add 1 to it, but I'm going to write 1 as 2x over 2x to make sure we have that common denominator there. So the 2x is going to cancel with this 2x, and finally we can see that our generating function t star of x, so that's all rooted binary trees, including the empty tree, is this expression, 1 minus root 1 minus 4x over 2x. And we'll come back to this in a bit, because our goal will be to try and determine a non-recursive formula for the coefficients inside this generating function. But we need a few tools to get there. And the tool that we need, the biggest tool that we need, has to do with a generalization of the binomial theorem. So if you remember, the regular old binomial theorem that we learned earlier, and you've probably seen this in many courses, probably in high school as well. If we have some expression, a plus b, to some natural number n, we can write that as I equals 0, the sum from I equals 0 to n of n choose I, a to the I, b to the rest, to the n minus I. And I'm going to rewrite this just a little bit. Note that if we have a binomial coefficient or a combination where we're choosing more things than we have, so if r is bigger than n, well, there's no ways of doing that. So whenever we have situations where the bottom bit in your binomial coefficient is bigger than the top, then that's just 0. So if we let this sum run over more values, instead of going up to n, we went up to n plus 1, n plus 2, all the way up infinitely far, all of those values past n are going to be 0, so I can just include them for, in some sense, for fun, but just so you can see how this is going to be analogous with the generalized binomial theorem. So I can view this as the sum from I equals 0 now to infinity of this expression here, because everything past n, all your terms are going to be 0 anyway, so I can just do that. And the whole idea, we're going to generalize the binomial theorem. Instead of having a natural number here, we're going to generalize this so you can put whatever real number you like here. So that's what's going to go down. So rather than for n, which is a natural number, we're going to let it be alpha, whatever real number we like. Okay, so to get there, we need a little bit of notation. And the first piece of notation that I want to introduce is called the falling factorial. And it's a generalization of the factorial. In some sense, it's a generalization of permutation. So it's a generalization of n factorial over n minus r factorial. So generalization of that. And what this means, this a with a superscript of k with a line under the k, so that's the notation there for the falling factorial. And what it means is starting at whatever number alpha you have, you just want to write k numbers that differ by 1 all multiplied together. So alpha times alpha minus 1 times alpha minus 2 all the way down to alpha minus k minus 1. Just to be clear, there are k numbers here. So just as a quick example, we can see that negative 6 following factorial 3 is negative 6 times negative 6 minus 1, so that's negative 7, times negative 8. So negative 6 times negative 7 times negative 8. And 1/2 following factorial 5 is a half times a half minus 1, so minus a half, times minus a half minus 1, so minus 3 halves, times minus 5 halves, times minus 7 halves. So 5 numbers in a row that all differ by 1. So that's how the following factorial works. And the whole point of defining this following factorial is to define a generalized binomial coefficient here. So we want to define alpha choose R, where alpha, rather than being a whole number, is any real number we like. And we're going to define it as the following factorial, alpha following factorial R, over R factorial. And remember that if alpha is indeed a natural number, then these definitions coincide. So n choose R using our generalized definition is n following factorial R over R factorial. But remember, n following factorial R for whole numbers, that's just n factorial over n minus R factorial. So that following factorial for positive whole numbers looks like that. And then we just have this R factorial here. So it's the exact expression for the regular binomial coefficient. So that's great. So this generalizes quite well. So let's take a look at a few examples here. So let's take negative 3 choose 4 using our generalized binomial coefficient. Well, here we're going to take negative 3 following factorial 4 over 4 factorial. So it's going to be negative 3 times negative 4 times negative 5 times negative 6 over 4 factorial. And we can simplify this a little bit, and it'll look fairly familiar to you. Well, we can take out a negative from each of these guys. So when we have negative 1 to the 4, in fact, that's just positive 1. And this looks like a standard binomial coefficient here, where we have 6 times 5 times 4 times 3, so we don't have 2 times 1. So this is like 6 factorial over 4 factorial, 2 factorial. And you can check, I said 10, but that's incorrect. This is 15. So that's how the generalized binomial coefficient works. Now, just like that little note I did above, we can show that if we ever put a negative whole number into the generalized binomial coefficient, then we can express it like this. We have negative 1 to the power of R times the positive version of the largest negative number in our following factorial, choose R. So let's see that. Let's see how this works. So here is negative alpha, choose R. So we're going to have negative alpha following factorial r, so that's going to be negative alpha times negative alpha minus 1, all the way down to negative alpha minus r minus 1 over r factorial. All of these have a negative that I can factor out, so I'll factor out the r negatives, and I'm left with alpha times alpha plus 1 times alpha plus 2, all the way to alpha plus r minus 1. And what's that? That is indeed alpha plus r minus 1 factorial, except we don't have the last alpha minus 1 term. So we can divide by alpha minus 1, and then we have this r factorial here. But this is the same expression as alpha plus r minus 1. Choose r. We're choosing r things, and we're not choosing the remaining alpha minus 1 of them. So we have r factorial and alpha minus 1 factorial in the denominators here. So when you have a negative number for a generalized binomial coefficient, we can indeed simplify it quite a lot. And it really depends on what r is here. R still has to be a non-negative whole number. But depending on the parity of r, if r is odd or even, it's going to affect whether this generalized binomial coefficient is positive or negative, because you get r copies of negative 1 multiplied by your expression. So if r is negative, then you're going to have this expression be negative 1. So when I was making these notes, I thought that we would indeed use this lemma here. But the approach that I took below ends up not using it. So we don't actually need this small lemma, but it's still worth doing as an exercise. So there's a nice relationship between generalized binomial coefficients of this type and some coefficients here. So you should be able to show that this indeed does hold. And I'll leave that as an exercise. But now that we built up generalized binomial coefficients, we can indeed talk about the generalized binomial theorem. So, we need 3 real numbers. We need alpha, that's going to be our power, and then we need our things in our binomial, a and b. So if we have those guys, then a plus b to the alpha, we're going to represent as this infinite sum, as k equals 0 to infinity. And it's going to look exactly like the regular binomial theorem, except the regular binomial coefficient is replaced by the generalized one. Note that there's not even different notation here, because the generalized binomial coefficient agrees with the regular binomial coefficient when you have a non-negative integer here. Then we don't need different notation. So it looks the exact same. We just have to use the idea of the generalized binomial coefficient. And I will say, we're not too worried about it for our purposes, but this all makes sense. This will converge. I will say that in the proof of this, I'm going to be thinking about b as my variable, and a is just going to be some sort of constant. So I'm thinking about b here as my variable. In fact, below I'm going to replace it by x, just so we're thinking in the right way, because we're used to using x as a variable in calculus. So, as I said before, b is going to be our variable, and for ease of readability, we're going to call b x. So I'm going to look at a plus x to the alpha. Now, the whole idea here is using the idea of Taylor series to expand this as an infinite polynomial. And remember, for Taylor series, our coefficients for x to the n, and our Taylor series is going to be centered at x equals 0. So really a Maclaurin series, if you wanted to use that language. So our coefficient is given by the nth derivative at 0 over n factorial. So that's the coefficient for x to the n. Okay, and again, if we're really talking about expressing this function here, which I guess I should call this f of x. So when we're talking about Taylor series, this is only true really if this converges, and we can say that the remainder converges to 0. But for our purposes, we're not going to worry about that. We're just thinking about this formally anyway, really. So we're not super worried about checking convergence. But let's use the idea of Taylor series to figure out the nth derivative. So let's go ahead. Well, the 0th derivative, that's easy. That's just do nothing. It's just a plus x to the alpha. And you can see here that we could use a very easy chain rule here. And in fact, the chain rule is fairly easy since the inside has derivative 1 anyway. We can just view a plus x as a variable. So the first derivative, we're going to multiply by the power and subtract 1. So we get alpha times a plus x to the alpha minus 1. Second derivative, do it again. So we have alpha times alpha minus 1 now. Subtract 1 from the power, a plus x to the alpha minus 2. Third derivative, a times alpha minus 1 times alpha minus 2 times a plus x to the alpha minus 3. And we continue on. And we can see what's happening here. We're seeing a falling factorial of alpha appear as your coefficient for a plus x. And we note for the first derivative, we have the first falling factorial of alpha. The second derivative has the second falling factorial. The third derivative has the third falling factorial. And the nth derivative will have the nth falling factorial of alpha times a plus x to the alpha minus n. Great. So remember, for our coefficient of our Taylor series or Maclaurin series, we need to evaluate the nth derivative at 0. That's no big deal. We do it, and we get alpha falling factorial n times alpha plus 0. Remember, we're letting x equal 0 here, to the alpha minus n. So simplifying that, we get alpha falling factorial n times a to the alpha minus n. So it's starting to look like our binomial theorem already. So now let's plug in that nth derivative evaluated at 0 into our Taylor series formula. So here it is here. So we have alpha falling factorial n times a to the alpha minus n over n factorial times x to the n. Remember, we're thinking of x as b here. So we'll rearrange so it looks more like what we want. So let's move this alpha falling factorial n with this n factorial, because we know that that is indeed the generalized binomial coefficient. Alpha, choose k. And what do we have left over? A to the alpha minus k, b to the k. I just changed b to x and n to k to look more like the expression that was written down first. That's just a swap of variables. There's no real mathematical change going on there at all. So that's pretty nice. So let's see a few examples here. So let's look at the expression 1 minus x to the minus third. And this looks like this generating function in some sense. So you can imagine something similar may pop up at some point in your combinatorial career. But let's write this down. So this is going to be alpha choose k, so -3 choose k, times 1 to the -3 minus k. Well, that's just going to be 1, so that just goes away. And then we have times minus x to the k. Okay, so we note here we can use that simplification of the generalized binomial to change this guy here, -3 choose k, to the positive expression 3 plus k minus 1 choose k times -1 to the k. So they're the same expression. That's just using that little simplification. And then I'm going to factor out a -1 to the k out of this minus x to the k. So there's that there. And you should notice that we have -1 to the k times -1 to the k, so we'll have an even number of -1s, so they'll just go away. So we can express 1 minus x to the -3 as the following infinite polynomial. 3 plus k minus 1 choose k times x to the k, where of course k goes from 0 to infinity. And let's write down the first few terms here. So we have 2 choose 0, x to the 0, plus 3 choose 1, x to the 1, that's when k equals 1, plus 4 choose 2, x squared, plus 5 choose 3, x cubed, plus 6 choose 4, x to the 4th, just replacing k with the next number every time. And to see these as numbers, if you like, we have 1 plus 3 plus 6 plus 10 plus 15, multiplied by the respective powers of x, of course. And I just want to point out that I can view this in the following way. So 3 I can view as 1 plus 2. 6 I can view as 1 plus 2 plus 3. 10 I can view as 1 plus 2 plus 3 plus 4. 15 I can view as 1 plus 2 plus 3 plus 4 plus 5. So you can see here that what's coming out of this is they're called the triangle numbers, because you can view this as 1 dot and then 2 dots, so that's 3 dots. Here's 6 dots. Here's 10 dots. Here's 15 dots. So a triangle made out of this many dots. So that's pretty interesting. So this series here counts the triangle numbers. That's very interesting. Okay, let's look at this. Let's find the first 5 terms of 1 plus 4x to the 1/4. So we'll have a fractional exponent here, and we'll deal with another fractional exponent later on as well. So we know that this is going to be the sum, as k goes from 0 to infinity, of 1/4 choose k times 1 to the 1/4 minus k times 4x to the k. And the first thing you notice, of course, is that this is just 1 to some power, so that just goes away. That's just 1. And maybe it'll be helpful to expand this 4x all to the k out as 4 to the k x to the k. So I'll rewrite this as the sum from k equals 0 to infinity of 1/4 choose k times 4 to the k x to the k. Great. Okay, so we want the first 5 terms. So let's just write them down. We want 1/4 choose 0, so this is when k is 0. 4 to the 0, x to the 0, plus you can imagine the other ones, 1/4 choose 1 times 4x plus 1/4 choose 2 times 4 squared x squared plus a quarter choose 3 times 4 cubed x cubed, and then finally a quarter choose 4, 4 to the 4th, x to the 4th. Okay. And I'll leave that simplification. You should work this out to be actual numbers, but I'll leave this as a little exercise to continue. Just simplifying a quarter choose 0, a quarter choose 1, a quarter choose 2. And I will just say, when you have this quarter here, you can imagine that when you do the following factorial, you're going to get lots of powers of 4, and they're going to cancel with this power of 4 here. So a nice simplification in this case will happen. Okay, so we understand how the generalized binomial theorem works now. So if you remember, in our generating function for t of x, remember t of x, or I guess t star of x, was 1 minus square root 1 minus 4x all over 2x. So in order to simplify this, we're going to use the generalized binomial theorem here to simplify this guy, and then plug that simplification in to the rest of it to simplify the entire generating function. So that's going to be our plan. And we're going to do quite a bit of work here because some nice simplifications happen. So we get something of a really nice form. So let's go ahead and look at this. So we're just going to use the definition of the generalized binomial theorem here. So this is going to be 1/2 choose k times 1 to the whatever. That's going to go to 1 anyway, so we don't need to worry about that. Times negative 4x all to the k. So the next thing we're going to do is I'm going to factor out this minus 4 to the k. So let's see that on the next slide. So I do so. I factor out this minus 4 to the k separately from this x to the k, but otherwise this is the same thing, just 1/2 choose k. Now, remember, 1/2 choose k, this is just a half following factorial k over k factorial. So I'm going to write that out because I want to take out a lot of common things here. So I'm going to write down the numbers starting at a half and then decreasing by 1. I'm going to come up with the k consecutive one. So a half times negative a half times negative 3/2. And you can check this goes all the way down to minus 2k plus 3/2. So there indeed is our k numbers in our following factorial. So, noting some stuff here, I'm going to notice first that this half itself is kind of weird. So I'm going to think about that almost a little bit separately. But otherwise, I start at a half, and then I go 3/2, so negative a half, negative 3/2, all the way up to negative 2k plus 3/2. So this half is just kind of a little bit strange, and otherwise I have k minus 1 numbers here. So what I'm going to do first is I'm going to factor out all of these 2's. So there's k copies of 2 here. So I'm going to factor them out, and I get a half to the k. So that's dealing with those guys there. K copies of 2. They all come out. And I have not quite k copies of negative 1. I don't have a negative 1 for the half. In fact, I have one less than that. I only have k minus 1 copies. So all of these negatives are taken care of by that. And what's left over in the numerator, maybe I'll just underline this in red. So what's left over in the numerator is 1 times 3 times 5 times 7 all the way up to 2k minus 3. So that's these guys here. So the product of all odd numbers from 1 to 2k minus 3. And I'm thinking, well, I have this 2 to the negative k, or a half to the k. I want to cancel that off if I can. And I have 2 squared to the k with some negatives involved, but that's no big deal. So I'm going to split this up as negative 1 to the k, 2 to the k, 2 to the k, so that's my negative 4 to the k. And I'm going to cancel off one of these 2 to the k's with this a half to the k, or a 2 to the minus k. And I'm going to cancel off all of these negative 1, so these k minus 1 negative 1s, with all but one negative 1 here. So there's one negative 1 left over. So that's that guy there. And I notice that I only have k minus 1 numbers here. So it probably makes sense to write this in terms of a product of k numbers. So what I'm going to do is I'm going to multiply and divide by the next number in the sequence. So I'm going to multiply and divide by 2k minus 1, and I'm going to divide by 2k minus 1 here. And then I'm left with the following thing. So I have this negative 1 times all the odd numbers from 1 up to 2k minus 1 multiplied together, times 2 to the k, x to the k, and then we're dividing by k factorial and this 2k minus 1. So it'd be nice to come up with a nice expression, because writing just the odd numbers multiplied together, that's not particularly simple. But I want to note the following thing. And that is that we're missing the even numbers here. So 2, 4, 6, 8, all the way up to 2k minus 2. And we could even tack on a 2k at the end. So in some sense, I'm going to multiply by 2 times 4 times 6 times 8 all the way up to times 2k. And I'm going to divide by that as well. So I'm going to simplify that expression in the following way. So a quick note is that I can view the numbers 2 times 4 times 6 all the way up to times 2k. Well, that's like multiplying the numbers 1 times 2 times 3 times 4 all the way up to times k, except we multiplied each of these numbers by 2. We have k copies of 2 here, so I'm going to factor all of those out, and I'm left with 1 times 2 times 3 all the way up to times k, which is indeed k factorial. So that's what I'm going to do, is I'm going to multiply and divide this expression by 2 times 4 times 6, whatever, times 2k, which is the same thing as multiplying and dividing by 2 to the k times k factorial. So I'm going to multiply by the actual numbers here. So 2 times 4 times 6 times 8 all the way up to times 2k minus 2 times 2k. And I'm going to divide by this expression written as 2 to the k minus k factorial, remembering that these are the same expressions. And again, I can see some stuff that will cancel. I see that this 2 to the k cancels with this 2 to the k, so we're looking pretty good. So what do I have here? I had this negative 1 over 2k plus, or 2k minus 1 just kind of hanging around. So I factored that out. You can see that in this expression up here. So this negative 1 and this 2k minus 1 in the denominator, I'll just take them out separately. And then, what do we have? Well, this is just all the numbers from 1 to 2k multiplied together. This is 2k factorial. And I have k factorial times k factorial in my denominator. And then I just have this x to the k left over. So what is this expression? Well, this is 2k, choose k. I'm choosing k things and I'm not choosing the rest, which is the other k things. So this expression simplifies very nicely to minus 1 over 2k minus 1 times 2k choose k times x to the k. So that's great. I've simplified. Remember, what was this? This was the simplification of 1 minus 4x to the half, because that appeared in our generating function. So we're going to use that on the next slide to simplify our generating function for t of x. So let's go ahead and do this. We had this t of x. Actually, it's t star of x. So I'll put my star there. We determine that's 1 minus root 1 minus 4x all over 2x. We simplified this root 1 minus 4x by the following Taylor series. So now we have these nice coefficients here in a nice form. And I'm just going to do a little bit of algebra to simplify this even more. Well, I'm going to take out a 1/2 x to the minus 1 from this expression here. So I'm just left with 1 minus this generating function on top. Okay, great. So that's just taking this 2x from the denominator and putting it to the outside. That's all that this is here. And the next thing I'm going to do is I'm going to peel off this first term. So remember that when k is 0, anything choose 0 is 1. So we're going to get -1 minus -1 here if we plug in k equals 0. So this simplifies to 1. Then we get 0, choose 0, so that's 1. And then x to the 0, that's 1. So when k equals 0, this expression is 1. So I'm going to peel off that, put it out here to cancel off with this one. And then I just have the index now going from k equals 1 to infinity of this guy. The 1 and the minus 1s cancel, so I'm just left with this expression here. Good times. Let's keep going. So next, I'm going to multiply this x to the minus 1 back in to this expression here. So I'm going to have 1 less x's. So I'm going to go from x to the k to x to the k minus 1. And then remember, our generating functions or our Taylor series always start at index 0. So I'm going to re-index this to start at 0. I'll call my new index variable m, and m is going to be k minus 1, which means that whenever I have a k, I can replace it by m plus 1. So starting at m equals 0 and replacing all of my k's by m plus 1s, I get the expression 1 over 2m plus 1 times 2m plus 2, choose m plus 1, x to the m. And that is, of course, this expression here is just 2m plus 2 factorial over m plus 1 factorial, m plus 1 factorial in the denominator. So we're almost done our simplification here. We can simplify this to be even nicer. So on the previous slide, I'm going to split things up. So remember, we had this 1/2, and then I had 1 over 2m plus 1. And then I had 2m plus 2 factorial over m plus 1 factorial, m plus 1 factorial. In fact, maybe I'll write that down to say where everything came from. So we had a half, and then we had our sum, and then we had 1 over 2m plus 1. And then I'll write this in terms of factorial. So we had 2m plus 2 factorial, m plus 1 factorial, m plus 1 factorial, x to the m. So First, I want to cancel off this 2m plus 1, so I'm going to need a 2m plus 1. And so where is that going to come from? Well, it's going to come from this 2m plus 2 factorial. So I'm going to split this up, this 2m plus 2 factorial, into 2m plus 2 times 2m plus 1 times 2m factorial. So that gives me access to this 2m plus 1 here. So that'll cancel with this 2m plus 1. So I group them together. And they cancel. Great. So now I have this 2m plus 2 term here. And I note that, well, that's just m plus 1 all times 2. And I have this 2 in the denominator here. So I have 2 times m plus 1. In my denominator, they'll cancel off with the 2m plus 2 in the numerator. So this cancels off to 1. So that's great. So what do I have left? I have 2m factorial over m factorial times, in the denominator, m plus 1 factorial. But I'll take the m plus 1 out, so I'll rewrite this as m plus 1 times m factorial. That's m plus 1 factorial. So I have 2m factorial over m factorial, m factorial. That's changing it back to n's instead of m's here. That's 2n, choose n. And I have this m plus 1 term left over. That I'm just going to write here as n plus 1, just because I'm changing the name of the variable back to n. So we've simplified this into a really nice formula. So we have that our coefficient for our generating function t star of x, remember that was our generating function, t star of x, each of these coefficients is given by 1 over n plus 1 times 2n, choose n. So that is very, very nice. And something that we'll see in this course is these expressions, this non-recursive definition for these numbers will come up again and again and again. In fact, these have a name. They're usually called C of n, and they're called this is the nth Catalan number. And now that we have this idea, let's count a related object and show that these numbers kind of appear everywhere. We're not going to count it directly. What we're going to do is we're going to come up with a bijection between rooted binary trees and the things we want to count, which are balanced binary trees. And the reason we call them balanced is because if you do have a child, you have 2 children. So rather than just something coming off of the left or the right is a possibility, if something comes off, it comes off in both directions. So you can't have just that, or you can't have just that. So they're no good. It has to look like that. And for this one, it makes sense to not talk about an empty tree, and we'll see why in a second. Okay, so let me show you a few examples of how these look. And we'll call this class script B for now. So these are all balanced binary trees. You can see this vertex has 2 children. These vertices have 0 children. So this has 2, this has 0, this has 2, 0, 2, 0, 0. So it's all either 2 children or no children. And you can check. Same with these guys. And we want to have just the root here as well. But we don't want the empty tree. For this, we don't want to count the empty tree, and you'll see why. Okay. So, here's my question to you guys, and think about this for a while rather than just going on with the video. But, is there a bijection to another class that we've enumerated? Do these look like something else that we've talked about. So maybe pause the video and think about that for a second. Think if you can come up with a bijection between these balanced trees and some other object. So, now that you're here, hopefully you thought of this following bijection. And it's a bijection from balanced binary trees just to these rooted regular binary trees. And the way to think about it is as follows. Every kind of vertex in a regular rooted binary tree corresponds to one of these shapes. So one of these vertices with two children off it in the balanced binary tree. And that kind of makes sense. If you think about it, what's going on with the root in a regular binary tree? By a root, I mean a vertex. Well, we can either append something to the left or append something to the right. So really, we can think of just like little bits coming off here where we can append another vertex if we like. So maybe I wanted to append something to the left here, so I'd append this, and then I would just join it up. So really, I'm thinking of the vertices in the regular binary trees with these sets of three vertices joined by the two edges in balanced binary trees. So to make the bijection more explicit with an example, suppose we had this regular rooted binary tree. Here's our root here. So this one is the following. We have a left child, and then on that left child we have both a left and right child. That left child has no children. The right child has a left child, and that's it. So this corresponds to the following balanced binary tree. So here's our bijection here. So this vertex corresponds to this bit of our balanced binary tree. Maybe we'll call it a structure just to give it a name. So I'm going to call this a structure. So this vertex, blue vertex, corresponds to this blue structure. And then, so we append on to the left, rather than over here we appended on a vertex. Here we're appending on a structure. So we plop that structure down. And we had a child to both the left and right over here. So here we're going to have a structure to the left and right. And here on the right child of the yellow vertex, we had a left child. So on this, the red structure, we're going to append a orange structure on the left bit. So you can see that these regular rooted binary trees are just these balanced binary trees, just written in a different way. And the other correspondence is we're going to correspond. In T, we have the empty tree. That corresponds to just the one root in balanced binary trees. So without any work, except realizing the bijection, and I just want to say we weren't super careful about showing this bijection, but for the purposes of this course, that's enough just saying the bijection is there. If you want to be super rigorous, there's still a little bit to prove here. But rather than parameterizing by the number of vertices in the regular rooted binary trees, for the balanced one, we're going to parameterize by the number of structures. So that generating function, b of x, is the exact same as the generating function for t of x. The only difference is x no longer stands for a variable denoting the number of vertices. Now it denotes the number of structures. And I'll leave as a little exercise. Well, we can, in fact, modify this generating function just a little bit, or even the version where we explicitly give the coefficients. So this version, 1 over k plus 1, 2k, choose k, x to the k. So we can modify this version here. Rather than to be parameterized by structures, we can parameterize it to count vertices. Just realizing a couple of things is that we always start with that root, that one vertex up top, no matter what. And whenever we add a structure, rather than adding one vertex, we add two vertices. So the number of vertices always changes like that. So you start with 1, and then you add an even number of vertices to get an odd number of vertices overall. So you can indeed modify this just a little bit to parameterize by number of vertices as opposed to number of structures. But I'll leave that as a little exercise in case you're interested.